So in this video, we're going to talk about the SymPy library. So we talked about it a little bit in class before, just as a preview. It's a symbolic mathematics library. Okay, so what that means is that we can take a variable x and treat it like a mathematical variable, not have to assign a value to it. We can search for it. Okay, same thing in things like pi. It will leave pi as the concept of pi, not the realization of any particular number of pi. Okay, so it really allows us to do some things that we just really couldn't do before, not in as simple of a manner, automatically. So if you're taking an algebra class or a trigonometry, a pre-calculus class, or a calculus class, even an advanced calculus class, then you should be able to use this to verify the answers. Okay, it's not going to do your homework for you, and it's not going to give you the steps involved, but it is going to be able to verify what's going on. Okay, and if you're using calculus in the real world, using any of this mathematical stuff in the real world, it's a quick way to do these calculations. Okay, so there are bunches of other libraries here that use the SymPy. Okay, so if you're in a particular class or a particular field, then you certainly can go and find those as well. Okay, so as far as the feature set, it's pretty gigantic, and I'm on the SymPy website here, which is at sympy.org. So it goes through some of the things that we can do. Okay, so we can, of course, do all the basic arithmetic. We can do simplification of trigonomic expressions and also polynomials. Okay, we can expand those. Okay, we can do factoring, things like that. We have all kinds of functions that you can imagine. Substitution, where we're able to take the value of a variable and apply it to some kind of expressions, things like that. Okay, it can do pattern matching. Okay, with polynomials, it can do factorization, which is really cool. It can do calculus, where it can do limits and differentiation, integration. It can do series. Okay, it can solve equations, whether they're differential equations or polynomial equations or systems of equations. Okay, if you're taking a discrete mathematics class, we can do different combinatorics. Okay, with the permutations and combinations and subsets and all that stuff. Okay, we can do binomial coefficients. We can do number theory. We can do all kinds of matrix things, the eigenvalues, eigenvectors, if you take a linear algebra, the determinants, inversions, all those things. Geometry, it has a lot of the built-in shapes, such as circles and ellipses and polygons that you can create. You can do intersections, tangency, if it's tangent or not. Similarity, there's built-in plotting built in, so you can do the 2D and 3D, different kinds of plots, which are kind of cool. There's some stuff built in for physics. Okay, there's some statistical functions built in, cryptography function that's built in, including RSA, which is a big one. We can convert from Python objects to SymPy objects, things like that. And then there's some printing functions which make it look nicer. Okay, so as far as some examples of this, I think I have to share and share again to get to that. If you're using this in Colab, okay, did that really do anything? Oh, it did, but I just can't see it on my screen. You can see it on your screen, but I can't see it on mine. There we go. We've got it now. Okay, so to use this, we can just import it directly. Okay, we don't have to install anything, which is good. Okay, now I've noticed after I did my example, a lot of people look like they were using the SymPy as SP, not SY. So you may want to make that change. It doesn't matter what you want to call it. Okay, so in this first example, what we're doing here is that we're creating some SymPy symbols. Okay, X, Y, Z, and N gets used in one of the examples here. Okay, so when we create that, it's not going to be a Python variable. It's going to be a mathematical variable. It's an abstract concept. Okay, I can then create an expression here. This is Python code. I'm saying x squared plus 5x plus 6. Okay, I can then use the pretty print, pprint, part of the SymPy to print that out. Okay, then I'm putting in a line, and then I'm going to go ahead and factor this expression. Okay, If it can't factor it, it just returns the whole. Okay, so it doesn't give an error. It just doesn't, if it doesn't give you an answer, it means it couldn't do it. Okay. And then I'm going to plot that. There's a plot feature built right in. Okay. So this should be a parabola of some sort. Okay. When we draw it, you run it, runs pretty quick, surprisingly. Okay. And we can see here that I'm printing out first the expression, and it puts in the x squared plus 5x plus 6. So it looks like math, not like Python. Okay. Factoring that into x plus 2, x plus 3. If you work that out, you will find that's the correct answer. And then real quick, it gives us a pretty basic, but it gives us a chart here, okay, of the x at the bottom and the fx, so the value at the functions at the top, okay? So it's kind of nifty. So here's another example. We've got, in this case, x cubed plus 3x squared plus, no, x squared plus 3x 2y, okay, plus 3x, no, sorry, read it again. X, it'll probably print it for me. Yeah, I'm going to print the expression. Then it's going to factor it. Let's just print the expression. That's hard to read out loud. There we go. X plus 3xy plus 3xy. No, 3x squared y plus 3xy squared plus y cubed. That's what it is. X cubed plus 3x squared y plus 3xy squared plus y cubed. Okay. When you factor that, that is x plus y cubed. Okay. That's that simple as can be. Okay, so we have this expression. Okay, so going to print that out as well. It's x times x plus x times y plus x times y plus y times y. Okay, and we're going to substitute x being 1, y being 2, and see what we get. Okay, so we get the x plus 2xy plus y. Okay, squared, sorry, x squared, that's x plus times x is x squared plus 2xy plus y squared. And we substitute in a 1 and a 2, we get back a 1. Okay. We have another x minus 5 minus 7. This expression, we assume that's going to be equal to 0. We can then solve that, okay, and get the 12 as the answer. Okay. Quick and straightforward. So here's another we're going to solve. We've got x squared plus 5x plus 4. Okay, we're going to solve that one with the sy.solve on the expression, but then we're going to print out the results there. Okay, so in this case, we have 2 answers. Okay, these are the roots or the zeros of the system. Okay, you normally would factor these and then get each part could be a 0. Okay, in fact, if we wanted to, we could also factor this expression just to check our answer. Okay, so I could just say sy.factor expression. Okay, if I do that, that's weird. It didn't print everything out like it didn't give me the that should be, yeah, I don't know why I didn't do that. Let's see. The printing is sometimes a little weird. I guess I could do something else. I could do like f is equal to that, and then I could do sy.p print f, and then print just to make it nicer. Yeah, okay, so that's going to factor it out to x plus 1, x plus 4. Okay, then it prints out the equation. And then from that, it's clear to see that these are the zeros. If it's -4, that's a 0. It's -1, that's a 0. Okay. Then we can simplify expressions. We have here x cubed plus x squared minus x minus 1 over x squared plus 2x plus 1. Okay. And if you would do all of the factoring and canceling out and all that would simplify to x minus 1. Okay. You can also, if you have a polynomial expression, we have x plus 3, x plus 2. Okay, I think we saw that one before. We can go ahead and it will automatically expand that out to the x squared plus 5x plus 6. Okay. We can also simplify using this trig simp. We have here, there are built-in sine and cosine functions here, again, that don't evaluate to numbers. They keep them as a symbolic idea. So we've got the sine x squared plus cosine x squared, okay? So we can simplify that, which just simplifies to 1, okay? And if you know trigonometry, you would know that that would be the case, okay? You can also rewrite using another form. So in this case, I'm going to rewrite tangent x in terms of sine x, okay? And it does that for us as 2 sine squared x over sine of 2x, okay? We can solve systems of linear equations. So here we have an expression 1, 2x plus 3y minus 6, expression 2, 3x plus 2y minus 12. I can use this sy dot solve of the two expressions. I'm not sure why I want the dictionary to be true, but I do, and it works, okay? I'm then going to print out the expressions and then the answer, okay? I guess that's putting that in the form of a dictionary, okay? So in this system, x would be 24 divided by 5, and y would be -6 divided by 5, okay? We can also do calculus. So here we have calculus calculating the left side limit, the minus sign here, okay? So my expression is absolute value of x over x, okay? I'm going to print that out. I'm then going to calculate the limit to be the sy dot limit of the expression, okay? Starting at 0, x going to 0 in a negative direction, and then print out the results, okay? So the limit there is -1, okay? We have the series here. We're doing n squared, the series of n squared from 0 to 100. So 0 squared plus 1 squared plus ... 100 squared, okay? So I'm going to do the summation here, the sy dot summation of n squared starting at n, or using n, starting at 0, going to 1,000, okay? When you do that, it will calculate that summation for you, and you can certainly get more complicated ones, okay? We can do differentials in calculus 1. So in this case, I have a simple expression, x squared plus 2x plus 10, okay? And I want to do the differential in regards to x, okay? So this is pretty easy to do in your head. It should be 2x plus 2 should be my answer, okay? So it's going to print out the expression again, and then print out the results, okay? You can also do an integral, okay? So the integral we're doing here is the cosine of x cubed of x dx, okay? So we're going to integrate that out as well, okay? Set it equal to I. We're going to print the original expression. We're going to print the integral of that. And we're then going to plot out the answer because plots are easy, okay? So here's our problem, the cosine of x cubed, okay? The integral of that is going to be negative sine cubed of x over 3 plus sine of x, okay? And here's the chart that we created from that, okay? Which is pretty interesting, okay? So this is a powerful tool, okay? Again, I would not use this because you see it doesn't give any steps. So it's not really something you can use to do your homework for you, but it is something that you can use to check your answers. Or if you need these kinds of calculations in your program, it's an easier way to get it for sure than other ways that you could do, okay? So if you have any questions on this, let me know tomorrow and we'll have a programming exercise using this in class tomorrow.